Hello, Dr. Keith Schubert, answering more questions that students sent to me. So this one is going to have to do with the class that was actually today, and it was on taking compliments and that. Now we are going to deal with compliments in future classes also, because it's you know it's a topic that a lot of people at first have a little bit of difficulty with. But I do want to get you a video so you can start thinking about the ideas. Let me just kind of briefly walk through our argument. Um, Now, what we really want to get to ultimately, let me give you the goal first. We want to get to something called the two's complement. And the reason we want to get to two's complement is that this is going to handle subtraction for us very nicely. That's what I want, right? Subtraction, I don't like how it does it because subtraction involves borrowing, and I could create a borrowing circuit, but that's just more complicated and slow. I'd really like to be able to use, and I'd have to build a specialized circuit. I'd like to just use my addition circuit. And we know for a fact on base 10, if I take numbers, like in class we did 25 and 17 in base 10, and we said, oh, to do subtraction of 25 minus 17, it's the same as 25 plus a negative 17. So I could use an addition circuit to do subtraction if I can put the minus on the 17. So that begs the question then, what does negative 17 look like? Well, we're used to just writing negative 17 as negative 17, and we're human beings, and we just process it. We've learned things, and you do it, and you don't really even think about it now. Now, what we're going to look at is how can we handle it in a different way. Now, human beings can basically fake pretty well infinite precision because we can consider as many digits we want. We just keep adding them on. Computers can't do that. Whatever you give them, they're stuck with. So when we're looking at these, I mentioned in class, hey, look, we've got two little digits. Imagine you've got a calculator with a display, and imagine it was a small display so that your calculator only had two digits on its screen. And I could type in the first number 25, and then I hit the minus and it clears out, right? Because that's now, and I put in the second number 17, I hit enter, and then the next thing it's going to show me is the solution 08 on the screen because it only has so many digits. Now we can look at this and say, okay, that involves me having to borrow because this 7 is bigger than the 5. I want to avoid that. Is there a different way I can do it? And what we kind of noticed, I'll give you a different way of thinking about this here. What if I started off with the idea of the number 100? Now 100, if I put it in my two digits, the only two digits that can show are the double zeros. So that 1, there's no screen for it, so you can't see it. So if I were to add 100 to any of these, it would make no difference because I'm adding two zeros. The 1 is not going to appear. So what I would like to be able to do is take this and handle my problem because this is a minus. So I'm going to add 100 to it. So if I do this and I go 100 minus 17, and I calculate that as an intermediate problem. So when I take this 100 and this minus 17, that ends up doing 83 as the number. That's 100 minus 17. But we know this adds up, right? 0 plus 5 minus 7, and 0 plus 2 minus 1 in the tens column. When I do these, I'll have to go borrow 1 from the other column if I was calculating this as a human, but I know it will give me 08 because I know 25 minus 17 is 08 and add zeros to it. It does no change. So far, so good? Hopefully. Okay. So therefore, if I break it up, it doesn't matter the order I do it in. So I just take the 100 and the 17. And there we go. And remember, I'm doing 100. Now, my intermediary calculation can have more digits than is shown. And we can make a circuit that can hold one extra bit while I'm calculating things. And this is what we'll actually do in some cases. We'll also have some other clever ways. But I can make the intermediate circuit a little bit bigger and then just truncate, throw off that extra digit at the end. That's what we're doing here. I do the 100 minus 17, I get 83. I put the 25 up top, and now it's addition. 5 plus 3 gives me 8. 2 plus 8 gives me 0, carry a 1, and there's nothing to hold it, so it disappears. And I get the correct answer because it's the same calculation. So therefore we say 83 is kinda like minus 17. So now I say I'm going to make a convention, right? Now, because 83 is also like 83. So we have to make a deal here. And we have to say you can either use 83 as 83 or you can use 83 as minus 17, but you can't do both in the same code. So we're going to make up a code, a set of rules for representing data. And in this version here, which is called the tens complement, my rule is if it's 50 through 99, because remember I only have 2 digits, these will be negatives. And if it's 0 through 49, these will be my positives. That's my rule. And anything on this upper half, that allows me to do this 100 minus the number less than 50, and I'll end up with the appropriate area. So I could have 49, 100 minus 49 gives me 51. It's in the negative zone. So hopefully that makes sense. What you'll notice is 50 or 100 minus 50 is 50. It flips back on itself. And we just choose that that's going to be the negative number because of our convention. So there's equal numbers on each side. And if you do 100 minus 0, you'll get 0 back in this case. But don't worry too much on the 100 side. I just want you to see roughly half go negative, and it's the larger numbers, and you get the other half are the positives, which is the lower half. And it's just a convention. So if I showed you the number 25, that since it's in the lower half, it means it's actually 25. Now, if I showed you the number 83, it's in the upper half. It's in the big number range. So therefore, 83 has to be a negative number because it's in the upper half. Now, if that makes sense to you, right? It's just a convention. 83, anything 50 and above is negative. We just look at the first digit. If it's 5 or bigger, then we say it's a negative number. Then to figure out what the magnitude is, I would have to do 100 minus 83. That would give me the magnitude. So 100 minus 83 would give me 17. I knew it was negative because it was an 8, so I get negative 17. So that's how I would flip back out of this convention to find out what does it mean to a human being. If that makes sense, because these are kind of numbers you're used to, we're going to do the exact same thing with base 2, except we picked 100 because it was a base 10 number. For us, this is powers of 10. However many digits you have, you pick a bigger and bigger base 10 number. And we said one way you could do base 10, and this is a fast, easy way to do subtraction because that was still slow. 100 minus 17, you'd still have to borrow. So I can represent 100 by 2 different numbers, 99 and 1. So what I'm going to do then is do 99 minus 17 and I get 82. And then I take 82 and add 1 to it, and I get 83. And then I take the 25 over, and I have my 25 plus 83, which gives me my 08. This kind of two-step process, while for a human you can go, oh, I can do 100 minus 17 easy, but it involves borrowing. This one, by going to 99 plus 1 equals 100, when I've got the maximum digit here, I don't ever have to borrow. That's the big key to us. I don't have to borrow. And I have to still have 100, otherwise it changes the number. So I then have to do take the 99 minus this, and then add 1 to it. That's the whole trick. And that gets me to the effect of 100. So if that's good with you, we're going to take that same idea and now apply it to binary. Now, in binary, we're not going to be looking at numbers that look like 99. We're going to have numbers like, well, let's actually do 25 and 17. So let's convert 25. And we'll convert 17. I'm going to erase this, so hopefully you've seen this enough that you're pretty sick of it by now. 25 divided by 2, it's odd. And so we get 12. 12 is even and gives me 6. 6 is even. I get 3. 3 is odd. I get a 1. 1 is odd. Nothing left over. So this number, reading it up and around, gives me 25 is 11001. Yay. That's 25 in base 2. 25 base 10 is equal to that. Okay, 17. 17 is odd, so it'll have a remainder of 1. Divided by 2 gives me 8. 8 is even. Divided by 2 gives me 4. I've been talking too long. Give me a sec to drink of water. All right. Thank you for the drink of water break. Feel a little bit better now. Okay. So 4 divided by 2 gives me 2, carry nothing. 2 divided by 2 gives me 1, carry nothing. And 1 divided by 2 gives me 0, carry a 1. Okay. Or 0, remainder 1, I should say. And I read it around, and I get 1, 0, 0, 0, 1. If you ever want to check these, you can see that these numbers, it's 1, no 2s, no 4s, no 8s, and a 16. So 16 plus 1 is 17. Now, I can put extra digits on here. This one also, it's 1 plus 8 plus 16. So 16 and 8 is 24 plus 1 is 25. It's a nice check to do. So 17 base 10 equals this. Okay. Uh, when I go to do these, I'm going to want some extra digits because we said the larger numbers. Remember, if the leading bit is 1, it's in the upper half. If the leading bit is 0, it's the lower half because we only have 2 possibilities for those. So just like with our numbers 50 and above, if it's a leading 1. Now, I don't want, this number is not negative, so I need to make my digits a little bigger. So I have to have at least a leading 0 for my positive numbers. So it's in the lower half. Because if it's not in the lower half of numbers, I'm in trouble. So this now gives each of these 6 bits. That's the least I can do to get a system that'll work for these. All right. So I want to do subtraction. Now it turns out that these ones will actually be very simple, no borrowing required in base 2. Just bad choice on my part. But let's get minus 17 by following our rules. So we're going to want to find minus 17. We said the equivalent idea in base 10 was we put the maximum digit on each. This is following that pattern. Maximum digit all the way across, and we subtract. All right, so 1 minus 1 gives me 0. 1 minus 1 gives me 1. 1 minus 0 gives me, I should say 1 minus 0. 1 minus 0 gives me 1. 1 minus 0 gives me 1. 1 minus 1 gives me 0. 1 minus 0 gives me 1. This is the equivalent of 99 minus 17. That's basically what we've done here, although this is not 99. So we're actually, that was our 16, so that's a 32's place. So we've got 0 through 63, so that's 63. But in any case, this is our number, but it's 1 less than the radix. So we call this the diminished radix complement or the ones complement. And remember, this is the intermediate step to get to the one we really care about, the twos complement. There's some very old machines that actually worked on the ones complement, but they had to do all kinds of extra little steps, and it's ugly, and pretty much nobody does that anymore. So I wouldn't waste your time. It's a thing that happened already in the 60s or 70s, so it's a pretty decent time ago. All right, so that's our ones complement. So we had to do this is our 63, the equivalent of our 99. We have to add 1 to get to one more 64, which goes to the next digit. Because remember, 1, 2, 4, 8, 16, 32, 64. So 63 plus 1 is 64. The effect of that is going to disappear, just like the 99 plus 1 did. That then gives us this number here plus 1, so we just put a 1 in that spot. We notice it's in the upper half. The leading bit is on, so that means it's negative. And then the magnitude of this is the equivalent of 17, because that's what we started with. So this is the equivalent of the tens complement, but our base is 2, so we call it the twos complement. Now, some things we can do to kind of check to make sure that this, I've asserted to you that this is true. I've given you a mathematical reason for it. You can just verify it just for fun. If I take the number 17, 0, 1, 0, 0, 0, 1, that's 17. I can add minus 17 to it. Minus 17 is 1, 0, 1, 1, 1, 1. Just copying from down there. I can add them together. I should end up with 0. 1 plus 1 is 0, carry a 1. 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 But I only have 6 digits, so that one disappears. Because remember, computers can't just add new hardware to store things. I gave it 6 digits. I said, that's all I've got. That's all I get. If I say it's 8 digits, that's all you've got. You've got 8 digits. We have to extend everything out. But in this case, you can see 17 minus 17 works like a charm. And since all of our other numbers are based off that, if you want 1 above, it'd be 1 higher, so it's going to work. So you can just see from this, it's going to kind of work nicely. We'll do one other check, which is 25, our original problem. We said 25 minus 17. 25 is 0, 1, 1, 0, 0, 1. And minus 17 in 2's complement is 0, 0, 1, 1, 1, 1. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 1 plus 1 is 3. 3 is 1, carry a 1. Because 1, 1 is 3. So the low one goes here and the high one goes there. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. But I only have 6 digits. That one goes out. 1, 2, 4, 8. 16, 32. I have 1, 8. So the number's worth 8. Whee! Right? So it works for us nicely. So hopefully this kind of explained slightly different way. It's a similar argument by explained in a slightly different way. Hopefully that'll make a little more sense to you. If it made sense to you the first time and this doesn't, then stick with the one that made sense. So hopefully this does. If it still doesn't make sense, there's a lot of other ways to explain this, and I'm happy to do it, but I'm already at like 19 minutes, so I don't want to belabor it too much. Let me know if this makes a lot more sense when you're going on, and have a great evening.